This is an AQA Chemistry video, and it's all to do with the required practicals. I'm going to be taking you through the content, and then we'll be looking closely at past paper questions. In this required practical, we're being asked to make a soluble salt. So that's a salt which dissolves in water. And in terms of the reactants you'll need both an acid and an insoluble metal oxide or metal carbonate. In the example I'm going to show you, we're making soluble copper sulfate. Think about the acid we'll need. That will be dictated by the sulfate, so we'll use sulfuric acid. And my insoluble reactant will be my copper oxide. Just so you know, if you're asked to make a salt which contains a nitrate, you'll need nitric acid. If you need to make a chloride, you'll need hydrochloric acid. And as we know in this example, to make a sulfate, we'll be using sulfuric acid. So always bear in mind the appropriate reactant. But what about our method for making this salt? You'll get a mark for mentioning the correct reactants. Make sure you include any suitable apparatus. So I'm going to say, for this example, add sulfuric acid and copper oxide to a beaker and stir. We want our insoluble reactant to be in excess, so continue adding copper oxide until it's in excess, and you'll see no more fizzing occurring, no more effervescence. We need to remove any unreacted copper oxide, so we're going to filter the mixture using a funnel and filter paper to remove excess copper oxide. Now our next step is to evaporate some of the water, so we're going to heat the mixture using a Bunsen burner and evaporating basin until the crystallization point has been reached. And then our last step is to allow our salts to dry. So leave to dry, and do specify how you're doing this on filter paper. So zooming out, here's my detailed method as to how I'm making copper 2 sulfate from sulfuric acid and insoluble copper oxide. I just want to show you the apparatus. So we've already reacted our copper oxide together with our sulfuric acid. We've made sure the copper oxide is in excess, so then we're using the filter paper and the funnel to remove any unreacted copper oxide, leaving us with a saturated copper 2 sulfate solution, which we've placed in an evaporating basin. This gets put on top of a wire gauze on top of a tripod, which has a Bunsen burner underneath. We're going to use that Bunsen burner to heat our solution in order to evaporate some of the water to reach that crystallization point. And then our last step is to leave those crystals to dry. This question is about making a soluble salt. Plan a method to make pure, dry samples of zinc chloride from zinc carbonate and a dilute acid. If we actually look at the equation, we're using zinc carbonate, we need an acid, and we're making zinc chloride. So what acid must it be? If it's a chloride, it must be hydrochloric acid. So there's our equation. So how do we make a soluble salt from an insoluble reactant and an acid? First of all, we want to add zinc carbonate and hydrochloric acid to a beaker. Do mention all the appropriate apparatus and stir. Remember, we need the insoluble reactant in excess, and no more fizzing occurs, no more carbon dioxide is released. That will also show that we have an excess. Now we need to filter using a funnel and filter paper. Why do we do that? To remove any unreacted zinc carbonate. So now we have a saturated solution. So we need to heat the solution in order to evaporate some of the water. Leave the solution to crystallize and dry. Make sure you specify something like filter paper, drying oven, a warm place. Name 2 other substances that can be reacted with a dilute acid to make zinc chloride. So we know the acid is HCl. Do not refer to zinc carbonate. Your other options are just simply zinc, the metal on its own, as well as zinc oxide. Let's now discuss titrations. Now, a titration is used to find the concentration of either an acid or alkali. And so what you do is you use a pipette to add a known volume of either the acid or alkali to a conical flask, as we see at the bottom here, and that substance will be the one that we know the concentration of. At that point, we want to add some indicator, which will change colour based on whether you have an acid or alkali. Our next step is to take our burette. We want to fill it with the other substance, so either the acid or the alkali. This will be the substance that we don't know the concentration of, and then we're going to slowly add that substance to our conical flask until the point of neutralization is reached and that indicator only just changes colour. A couple of things: we'll want to swirl the flask to ensure that the reactants are mixed. We'll want to place it on a white tile so that we can see the colour change. We want to only use a few drops of indicator. And in terms of rinsing, you need to make sure that you rinse your conical flask with water, distilled water beforehand, but you want to make sure you rinse your burette with the solution being used. So if you look at this page of my revision guide, it's worth learning this method off by heart. We're using a pipette, in this case, to add acid to a conical flask. Then we'll add a few drops of indicator such as methyl orange or phenolphthalein. We place it on a white tile, as I said, in order to see the colour change. We use our burette, which we've already rinsed with the alkali, to start adding that alkali to the conical flask and making sure we add it dropwise towards the end, swirling the conical flask to mix the reactants, and then we stop when the indicator changes colour. By doing this, we can find the volume of alkali needed to neutralise that acid, and then we can carry out a titration calculation in order to find the concentration of the alkali. And I'll show you how to do that now. One thing they do like to ask you is the advantages of using a burette. So the first thing is to say that you can add solutions in small increments. And secondly, they're more accurate than a measuring cylinder. In terms of the types of indicators which can be used to show the end point of a titration, the first indicator I want to mention is methyl orange, which is red in acid, yellow in alkaline. Phenolphthalein is colourless in acid and a beautiful pink colour in alkaline. You don't want to use universal indicator in a titration. It would be totally unsuitable, and that's because it has a range of colours, remember? Green and neutral, blue and strongly alkaline, red and strongly acid, and you have no sharp colour change, which is crucial if you want to see the endpoint of a titration. Here's a very typical titration calculation. So 20 centimetres cubed of hydrochloric acid we use to neutralise 25 centimetres cubed of 0.1 mole per dm cube calcium hydroxide. Calculate the concentration of the hydrochloric acid. Very, very typical question. Because we're after the concentration of the hydrochloric acid, just so you're aware, the acid would have been in the burette, whereas the calcium hydroxide would have been in the conical flask together with the indicator. Try and bear in mind what's going on with titrations. So I like to use this scaffold in order to answer these questions because it makes it super straightforward. You want to rewrite the equation and then create a table. You're using this formula triangle, and then you list N, C, and V. N stands for number of moles, C stands for concentration, V is volume. So we're after the concentration of hydrochloric acid. Here's my hydrochloric acid, so I'm going to put an X here because I'm after its concentration. Now put in the table all the other information they've provided. We have 20 centimetres cubed of hydrochloric acid, so there's the volume. Just be careful with units. We need that volume in decimeters cubed, so we divide that by 1,000. We have 25 centimeters cubed of calcium hydroxide, and then the concentration is 0.1. So initially we want to find the number of moles of calcium hydroxide, which we can see from our formula triangle is concentration times volume. So we just need to multiply those two numbers together to get 0.0025. Now to work out the number of moles of hydrochloric acid, check what's known as the mole connection, which means looking at the large numbers at the front of the formulae. It's 2 to 1, so we have double the number of hydrochloric acid moles. So we just multiply that number there by 2 to get 0.005. And then finally, to find concentration, we do number of moles divided by volume. This number divided by this number. You can do that in one step if you wish, to get a final answer of 0.25 moles per dm cubed. This question is about citric acid. Citric acid is a solid. A student investigated the temperature change during the reaction between citric acid and sodium hydrogen carbonate solution. This is the method used. Pour 25 centimeters cubed of sodium hydrogen carbonate solution into a polystyrene cup. Measure the temperature. Add 0.2 grams of citric acid. Stir. Measure the temperature. Repeat steps 3 to 5 until a total of 2 grams of citric acid have been added, and the student plotted the results. Here's our graph. Figure 6 shows an anomalous point where 0.6 grams of citric acid was added. This was caused by the student making an error. The student correctly measured the mass of citric acid, correctly read the thermometer, correctly plotted the point. So what could be the reason for this anomalous point? So we're talking about this point here. So we can see the temperature is too high. So one thing we could infer is that the temperature was measured too soon. We explain the shape of the graph in terms of the energy transfers taking place. Use data in figure 6. So initially what's happening is the temperature is decreasing, and when we have a temperature decrease like that, it means that the reaction must be endothermic. It must be taking in heat energy. And then we can see down here that when 1.5 grams of citric acid was added, because there's no further decrease in temperature, it must mean that all the sodium hydrogen carbonate has reacted. And as a result, the temperature increases as energy is transferred from the surroundings to the solution. A second student repeated the investigation using a metal container instead of a polystyrene cup. The container and cup were the same size and shape. Sketch a line on figure 6 to show the second student's results until 1 gram of citric acid has been added. The starting temperature of the solution was the same. Explain your answer. Okay, so this time we've got metal rather than polystyrene. Polystyrene is a much better insulator. So actually what you're going to find is that there's more heat loss to the surroundings with the metal cup. So you'll see a shallower gradient on our graph. So it only mentions going as far as 1 gram, so I'll only take it that far. But there's my shallower gradient. So let's explain it. Polystyrene is a better insulator, meaning less heat loss occurs to the surrounding. The student used a solution of citric acid to determine the concentration of a solution of sodium hydroxide by titration. The student made 250 centimeters cubed of a solution of citric acid at a concentration of this. Calculate the mass of citric acid required. So the first thing we want to do is find the number of moles. So we do concentration times volume. We have 0.05 as our concentration. Our volume, be careful, that needs to be in decimeters cubed, so I divide by 1,000. So there's my number of moles. And then the mass is given by number of moles times MR. The MR, let's add up these individual masses. We do 6 times 12 plus 1 times 8 plus 7 times 16 to get 2.4 grams as our final answer. This is part of the method the student used for the titration. Measure 25 centimeters cubed of sodium hydroxide solution into a conical flask using a pipette. Add a few drops of indicator to the flask. Fill a burette with citric acid solution. Describe how the student would complete the titration. So we want to add citric acid dropwise near the end point. We want to constantly swirl the flask in order to ensure our reactants are mixed. Use a white tile to view colour change more clearly. We have two reasons why burette is used for the citric acid solution. A burette is more accurate than a measuring cylinder, and it allows you to add the citric acid in small increments, literally dropwise. 13.3 centimeters cubed with 0.05 molar citric acid solution was needed to neutralize 25 centimeters cubed of sodium hydroxide solution. The equation for the reaction is this: calculate the concentration of sodium hydroxide solution. So I like to use this method. We're going to steal the equation, so write that down in the exam. We'll set ourselves up with our table scaffold. Here's my formula triangle. Pop in the information given in the question. We have 13.3 centimeters cubed of citric acid, so that's my volume. Just make sure you divide it by 1,000 to get it into decimeters cubed. We were told the concentration is 0.05. The volume of sodium hydroxide added was 25 centimeters cubed, and we're after the concentration. So we now have enough information to find the number of moles of citric acid, which we do by doing concentration times volume. So multiply those two numbers together. So that's our number of moles of citric acid. What about our number of moles of sodium hydroxide? Well, check the mole connection. It's 3 to 1, so we need to multiply this number by 3. And now we have enough information to find the concentration by doing number of moles divided by volume, this number divided by this number, and that's how we get our 3 marks. Right, electrolysis, just to remind you, it means splitting a substance using electricity. And because we're doing chemistry, what is the type of substance? It's going to be a giant ionic structure because we need our substance to be made up of ions. I'm sure you're aware of this, but when you look at an electrolysis chamber, you'll have a positive ion and a negative ion. And your positive ion is your cation, your negative ion is your anion. So here's a really standard electrolysis apparatus. We have the electrolysis chamber, which contains our electrolyte solution. So that's our solution of ions, our positive and negative ions. As I've already said, the positive ions are cations, the negative ions are anions. You'll have 2 electrodes. Now those electrodes tend to be made out of something like platinum or graphite. And why do we use platinum or graphite? Because we need something which is both unreactive and something which conducts electricity. So the electrodes have special names. The positive electrode is known as the anode, and that's going to attract the oppositely charged ion, so it's going to attract negatively charged anions. The negative electrode, the cathode, will attract positive cations. If we were to look at the electrolysis of molten lead bromide, and remember we need our substances to be molten or in aqueous solution so that the ions are free to move. Let's consider what ions we have. We have Pb2 plus and Br minus. So at the anode, so the positive electrode, because opposites attract, you're going to have that bromide being attracted. It forms diatomic bromine, so that's why you need to write Br2. Let's balance that. And then in terms of electrons, in order to balance that, this is our completed half equation. And because electrons are being taken away, we call that oxidation. What about at the cathode? So that's the negative electrode. The Pb2 plus will be attracted, forming Pb, so just lead. We'll need to add 2 electrons in order to do that. So reduction has occurred. Remember the mnemonic oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And don't forget to state observations. With your bromine, you're going to see a brown-orange liquid. With your lead being formed, you'll see a silver-coloured metal. Remember, if you have aqueous solutions, such as aqueous sodium chloride, the fact it's aqueous adds additional ions. It adds H plus and hydroxide ions, as well as the sodium and chloride ions. Do remember that it's the least reactive element which forms at the cathode. So here's your half equation at the cathode. And then the halogen will discharge preferentially at the anode. So this is what's going to happen at the anode. This question is about electrolysis. Molten sodium chloride is electrolyzed in an industrial process to produce sodium. Figure 8 shows a simplified version of the electrolysis cell used. So let's have a look what we've got. We've got our molten sodium chloride, which means we have Na plus and Cl minus ions. So remember that at the positive electrode, the anode, you're going to have chloride ions being attracted. So there's the half equation occurring there. And then at the negative cathode, your sodium ions will be attracted. So we can see reduction occurring, which is the correct half equation for the production of sodium. I've actually already done that. We need a neutral sodium being produced. It's this reaction here, which is reduction, because electrons have been gained. If you're not sure about electrolysis, because after all it is a difficult topic, do check out my other videos where I go through this step by step. A mesh is used to keep the products of electrolysis apart. Suggest one reason why the products of the electrolysis must be kept apart. Simply because you don't want the products to react to reform the sodium chloride. Which type of particle passes through the mesh in the electrolysis of molten sodium chloride? I talked about these already. We've got ions. Aqueous sodium chloride solution is electrolyzed in a different industrial process. 2 gases and an alkaline solution are produced. So what sets aqueous sodium chloride solution apart from before is, as well as the sodium ions and the chloride ions, we also have H plus ions and OH minus ions present. So which 2 ions are present in the aqueous sodium chloride solution in addition to sodium and chloride ions? Indeed, it is the H plus ions and the hydroxide ions. Name the alkaline solution produced. So when you have multiple ions present, when you consider the positive ion, it will actually be the least reactive element which discharges, which means it's hydrogen, leaving sodium ions over in solution. If you look at the negative ions, the halogen discharges preferentially, so the halide ion. So that's the chloride ion, leaving the hydroxide ion over. So what is the alkaline solution produced? It is sodium hydroxide. Explain how the alkaline solution is produced. You should refer to the process at the electrode. So I'm just going to write exactly what I've just been talking about. We're going to say that sodium ions and hydroxide ions are left in solution. Hydrogen ions are discharged at the negative electrode, which remember is the cathode. Let's write that half equation. So our hydrogen ions form H2 gas, and that's reduction because electrons have been added. Let's write what happens now at the anode. The chloride ions are discharged at the anode, so at the positive electrode. There's the half equation occurring there. Because electrons have been lost, we call that oxidation. Now we'll look at all the reactions to do with temperature changes, and that involves endothermic and exothermic reactions. Remember, endothermic reactions take in heat energy from the surroundings, and so as a result, the surroundings get cooler. So you'll see the temperature decrease when you measure that with a thermometer in an endothermic reaction. Exothermic reactions release heat energy to the surroundings. So the surroundings get hotter And so with our thermometer, we'll find that the temperature has increased with an exothermic reaction. It's very important that you're aware of that. Let's look at these energy level diagrams. So with our exothermic reaction, remember that delta H, our energy change, is negative. And what that means is that our products have less energy compared with our reactants. So do make sure that these reactant lines are higher compared with the products. The difference between those two lines is your energy change. Your activation energy, remember, is the minimum amount of energy required for a reaction to take place. With an endothermic reaction, delta H is positive, and as a result, your products have more energy than your reactants, so the product line is higher than that of the reactants. Again, you can find the energy change, and do make sure you can label that activation energy again. In terms of examples of endothermic reactions, we've got cold packs used for sports injuries. Exothermic examples include hand warmers and self-heating cans. Now, the way in which we can investigate the endothermic and exothermic reactions include the following. So we could add a salt to water, such as sodium chloride, the salt, we add it to water. Neutralization reactions, an acid reacting with an alkali. An exothermic reaction, the temperature will increase. Displacement reactions, so when a more reactive metal displaces a less reactive metal. And combustion reactions, which is all to do with burning fuels like the alkane methane. This is a really typical setup. So here we're adding sodium chloride to water. We've got a polystyrene cup which is acting as a good insulator, and that's going to prevent heat loss to the surroundings. We might choose to add a lid again to further reduce heat loss. When we add the two substances together, we'll want to stir to ensure that they're fully mixed so that a maximum temperature can occur. But the best thing to do here is to look at past paper questions. This question is about temperature changes. A student investigated the change in temperature of a solution when different masses of ammonium nitrate were dissolved in water. This is the method used. Measure 200 centimeters cubed of water into a polystyrene cup. Measure the temperature of the water. Add 4 grams of ammonium nitrate. Stir the solution until all the ammonium nitrate has dissolved. Measure the lowest temperature reached by the solution. Repeat steps 1 to 5. Okay, because the temperature's gone down, I'm just going to make a note there. It's obviously an endothermic reaction. It's taken in heat energy. Give the independent variable and the dependent variable. You must learn your variables. Your independent variable is what you change, and your dependent variable is what you measure. So check the methodology. We're using different masses of ammonium nitrate, so that's our independent variable. And then what's our dependent variable? What are we measuring? The lowest temperature reached. Table 2 shows the results. Plot the data from Table 2 on Figure 2 and draw a line of best fit. Let's take the data. Let's draw a line of best fit. Determine the initial temperature of the water. You should extend your line of best fit on Figure 2. Follow the instructions. It's telling us to extend our line of best fit, so that's what I'm going to do here. So we're looking at this temperature right here. We can see that we start at 18.8. Obviously, it will vary depending on your line of best fit. How do the results show that dissolving ammonium nitrate in water is endothermic? I already accidentally answered that because the temperature decreased. They talk about the lowest temperature reached. The student repeated the experiment 3 more times. Table 3 shows the results for 8 grams of ammonium nitrate. The student recorded the mean lowest temperature of the solution for 8 grams of the ammonium nitrate as this. Explain why the student included a plus or minus 0.3 degrees Celsius after the mean lowest temperature. So if you were to look at the data here, you can see that the range, if we take the highest value, which is 16.8, take away the lowest value, 16.2, to get 0.6. And then the uncertainty is plus or minus half of the range, so half of 0.6 is 0.3. And so we'll show how that works. We're going to take our mean value, 16.5, and then we'll add 0.3 to get that highest value reached, which was 16.8 degrees Celsius. Now we'll take away 0.3 to get 16.2, which was the lowest temperature. What type of error is shown by the results in table 3? This is called a random error.